For a long time, scaling laws transformed natural language processing. As models became larger, they suddenly gained new capabilities. But vision models were far behind. Even the largest vision transformers were only a few billion parameters, while language models had already crossed hundreds of billions. So this is the point where we should stop and ask the question. Can vision models scale the same way language models do? Because essentially the underlying transformer architecture of vision transformers and language transformers is the same. So what is the difference? So to explore this, researchers built ViT-22B, a vision transformer with 22 billion parameters, and the largest dense vision model created at that time. But scaling was not straightforward. When they tried to train large models using standard transformer design, training became unstable. Loss suddenly diverged because attention logits grew too large, causing attention to collapse into nearly one-hot patterns. So the key contribution is not just size, not just scaling, but how to make scaling stable. So three main architectural changes made this possible. First, parallel attention and MLP layers. So instead of applying attention and feed-forward blocks sequentially, both operate in parallel and their outputs are added together. So in the conventional transformer architecture, we have first we apply the self attention, and on top of it we add the feed forward network. So you can think of this as first communicating between the tokens using self attention and then using that knowledge to think. But here what we are doing is we are communicating and thinking at the same time. So this improves hardware efficiency and speeds training without hurting performance. Second, query key normalization. Layer normalization is applied directly to queries and keys before computing attention. This prevents exploding attention scores and stabilizes training at massive scale. Because if either of this query or key become too large, then vector the attention vector is going to converge to a one hot vector. So this is essentially going to destabilize the training. Third, removing unnecessary bias terms in attention projections and normalization layers. So these norm layers and attention matrices are going to be bias free, but this MLP and as a whole, the attention branch and the MLP branch have their own bias terms. So together these changes enabled efficient large-scale training across thousands of devices using model and data parallelism. So scaling law improves out of distribution robustness, transfer learning performance, semantic segmentation and depth estimation, and video understanding. And this means we can improve the performance of these vision models in a very much similar way how we improve the performance of these large language models by increasing the size. So we have essentially created a new transformer architecture which can very easily scale vision transformers.